Right, so we continue with frame forwarding methods that we have. I introduced store and forward switching and cut through switching. Right, with store and forward, basically we have the entire frame, the whole frame, from the structure of the frame, starting with the SFD up until we get to the FCS, is it? FCS of FSC, frame sequence check, FSC. Right, this is the entire frame. It needs to be received by the switch, processed, checked for errors, then forwarded. So frame rese rinofanira kusvika so that it gets forwarded. That is store and forward switching. It's very reliable, less errors because all the errors are being checked. With cut through, we only need to receive up to the destination MAC address. So as you can see, right, tabva pa-SFD apa, I think ndo patine destination MAC apa. Then we have source MAC. So frame parinosvika, the moment we know, the switch knows kuti destination MAC chi, it starts forwarding ipapo. That is cut through switching. Right? Harisvike kunoko, kune error kunoko. Kunooneka kuti kune error kunoko. It doesn't get there. The advantage of doing this ndeyekuti ma-frames, they are forwarded quick. Information inenge iri forwardwa much quicker. Right? Not much processing iripo, tongo forward. The disadvantage ndeyekuti if ma-frames ari kusendwa kana ane a lot of errors, ese anenge achingosvika achidrop. Ese anosvika achidrop because we are not checking ma-errors. Hatisi kusvika at this point where the errors are being checked. So store and forward, there is checking and verification of data integrity. Then the frame is forwarded with advantages coming for error detection. It also enables some quality of service features. We'll discuss QoS, very important. I think I'm introduced on chapter number 1 here. Can I see my case already? Okay, QoS. This is very important, QoS. Store and forward allows us to deal with QoS, that error checking, error detection, enabling QoS. Those are some of the advantages that come with store and forwarding. However, it comes with a higher latency. It means when you talk of latency, ideally, we need a very low latency for communication. Right? The moment phonetic in action, there is a reaction on the other end. Something here, on the other end, kind of a thing. That is a low latency. Ideally, if we are to have communication, that is what we need. If we have to transfer something, that is what we need. But with the store and forwarding, there is a higher latency because of needing to check every frame. It also comes with high CPU utilization. When you talk of CPU utilization, the processing power of the switch. So it slows everything. The processing power parinenge processor, richitsvaga error, richiprocessor kuti destination MAC, processor source, processor type, processor all the bits. It takes a lot of time. Those are the disadvantages of store and forward. Right, with cut-through switching, some of the disadvantages, not some, the obvious disadvantages, high error rates. High error rates because we are not checking any errors. Right, going to the text here to conclude, a big advantage of store and forward is that it determines if the frame has errors before propagating the frame. When the error is detected, the switch discards. Discarding frame with errors reduce the amount of bandwidth consumed by corrupt data. So this one we've explained already. Less errors advantage. Store and forward switching is required for QoS analysis on converged networks where frame classification for traffic prioritization is necessary. For example, voice over IP data streams need to have priority over web browsing traffic. Okay, store and forwarding, very important for prioritization of traffic. All right. We look at cut-through switching a little bit more. In cut-through switching, the switch acts upon data as soon as it's received. We've gone through that. The switch does not perform any error checking. We've gone through that. There are two variants of cut-through switching. Right? Cut-through switching, general definition. It does not check the errors. It checks the frame up until the moment you get to the destination mark. Araclo forward. That is the general definition of cut-through switching. However, with these two variants, we try to find a balance between checking my errors and having a low latency, right? Instead of just pushing up a destination to end as a packet ready, we are now trying to find balance with these two variants. We are now trying to find balance between prioritizing the speed forward my frames edu or checking my errors, reliability. Right. With fast forward switching, it offers the lowest level of latency by immediately forwarding a packet after reading the destination address. This is the definition that we gave. In fast forward switching, a variant of cut-through switching. Because fast forward switching starts forwarding before the entire packet has been received, there may be times when packets are relayed with errors. The destination NIC discussed the 40 packets upon receipt. Fast forward switching is a typical cut-through method of switching. So this one, the way we defined cut-through switching. However, we have another variant, fragment-free switching, which is a compromise between high latency and high integrity of store and forward switching. A compromise between the high latency and high integrity of store and forward switching and the low latency and reduced integrity of fast forward switching. The switch stores and performs an error check on the first 64 bytes of the frame before forwarding. Because most errors and collisions occur during the first 64 bytes, this ensures that a collision is not occurred before forwarding the frame. All right. So fragment-free switching is a variant of cut-through. It does not store the whole frame. With store and forwarding, the whole frame rinotanga rareceivewa raprocesswa, then we can forward. But with cut-through, we started with just the destination and tapped forward. However, with this variant, we check the first 64 bytes. And with the first 64 bytes, we can identify some of the errors, the collision that we can have with that frame. So it means it minimizes my errors a little bit. Store and forward, minimum my errors. Fragment-free switching, my errors, they'll be there, especially canary at the end, at the frame sequence check with the CRC checking. Kana kune ma errors ikoko, those are the errors that we have. But kana pana ma errors a collision within the 664 bytes, those ones will be detected frame row discard. So basically, that summarizes the two frame forwarding methods that we have. Frame forwarding, to forward information connect on a switch. That is basically what that is. Memory buffering on switches. This is very important memory buffering. Switch redu, we are not there yet, but we will learn about my specifications a switch. Patataura nyaya yekuti store and forward. Pandataura nyaya CPU utilization. Starting with CPU utilization, processing. A switch has an operating system. An operating system. It has processing power, RAM, right? Paunotenga switch, those are some of the things you need to know and understand. What are the implications yekuita low processing power? What are the implications yekuita low memory per switch? We are now going to buffers. Information needs to be stored. Per store and forward, the method you're forwarding. Where are you storing frame iroro? Where is it being stored? It means switch rako needs to have a memory. It needs to have a RAM. That is basically the processing memory. All those things. So understanding kwazvirikuva, it leads you as a specialist network in IT. Kuti tikati toda kutenga switch, haungotengi chero. Unoverenga maspecs, ozoti ndine network yangu inenge yakakura sei. Therefore, the processing power randichada rakawanda sei. The storage randichada paswitch yangu inofanira kunge yakakura sei. All that allowing me to create a network very efficient, which performs exceptionally. Memory buffering on switches. Why I was talking about Jason and Dataura is because of Nyama buffer. A switch needs a memory NIO so that it is able to perform my duties in buffering. Right. An Ethernet switch may use a buffering technique to store frames before forwarding them, or when the destination port is busy because of congestion. That's another thing. Memory, for example, you are sending information to, let's have our switch. Okay, let's put 2 ports. Let's put 3. Okay, 3 port switch and send around. I know a 4 port switch. Let's just put 4. So this is port number 1, 2, 3, 4. Let's say your information is being sent from port 1 to port number 2. So we're sending information here. Right. Information inobva PC. PC rosenda information yayo yakawanda yosvika paframe panapa. But probably port number 2 iri kureceive some information iri kubva kune rimwe port number 3. Meaning information iri kubva kuno ichamirira kuti information iri kubva ku3 itanga yaforwardwa paport number 2. Then there is a queue inoitika with this information ish. Yakamirira kuti information iri kubva ipinde yese ipere. Iforward. Panoitika queue, kana pasina buffer iri paswitch, all that information iri kubva from this PC will be dropped because hapana buffer. Iri kusenda iri port rinenge risiri available. All that information will be dropped. But kana switch rako rine buffer, and as a specialist, you consider that pawakatenga maswitch ako, it means there is a memory iri reserved yekuti kana port riri busy, riri congested, this switch can store all this information. Kuno kunotobva yosvika yobva yaitwa stored panapa. Then kana port free, yochibva mubuffer yoenda to the port. Basically, that defines what buffering is. Now, with buffering, we have 2 mechanisms that are used to handle situations where a port is busy, for example, or when a switch needs to process the frame, like process here, store and forward. It stores, processes, then forwards. Where is it storing? It's storing in those memory buffers. We have two types of mechanisms that we have, the port-based memory and the shared memory. I'm not going to go through this. It's a lot. The port-based memory, basically what it does, each port on the switch has its own dedicated memory. So if I go to the example that I just gave here, where's my cursor? It's down there. If I go here, for my ports, every port ring a buffer. It has implications of its own though. Right. So port-based, every port, it has a buffer. Frames received on a particular port are stored in the buffer associated to that port. So if I'm receiving frames on port number 1, port memory per port you don't store that information. However, it comes with the disadvantages. Since frames are transmitted in the order that they are received, if one of the destination ports is busy, then apana information no send to that port, even if other ports are available. Let me try to make it more clear. It is possible for a single frame to delay the transmission of all the frames in the memory because of a busy destination port. So with port-based memory, it has this disadvantage. Even if my ports are free, iwewe kana uri unoshandisa port number 2, since my friends gedu kana achitransfer to anoita queue, even if mamwe maport akaita free, kana pareceiverwa traffic, for example, I can do this. If traffic iri receiverwa paport number 1 up, iri kuya queue, if this port is busy and occupied in traffic E, you cannot use mamwe maports aya up until port iri buffer buffer zvapera zvese. That's a disadvantage of port-based memory. Right. Which can be solved with a shared memory. So instead of having my memory per my ports, we have a pool where all my ports can take that memory. So port E can I read the memory in a historian pool, meaning my ports, they are not tied up and are available. This is dynamic. Port number 2 can I have memory in a historical. That's the difference between port-based memory and shared memory. At the end of the day, it's all memory which is used for buffering. The main difference between the two, with port-based memory, you can have a situation where all my ports are still functional because of one port recongested. Kana port iroro unoshandisa memory yayo, you cannot forward anything. Disadvantage. Right. Shared memory buffering also results in large frames that can be transmitted with fewer, we are right here, with fewer dropped frames. This is important with asymmetric switching, which allows for different data rates on different ports. Therefore, more bandwidth can be dedicated to certain ports. Right. Memory buffering on switches, clear. Duplex and speed settings. Two of the basic settings on a switch are the bandwidth and duplex settings for each individual port. It is critical that the duplex and bandwidth settings match between the switch port and the connected devices. We already discussed duplex settings, half duplex, full duplex. Half duplex sending in one direction, full duplex bidirectional communication. bidirectional communication, sending and receiving simultaneously. We have what we call auto negotiation, an optional function found on Ethernet switches, which enables devices to automatically negotiate the best speed and duplex capabilities. Why is it important discussing this at this point? Because what happens if, for example, one end of the switch, it has half duplex, and the other end, it has full duplex. And these two ports are trying to communicate with each other. What happens then? That's a problem. We are going to have congestion there, collisions. Because if this one is sending, since it's in half duplex, it means it cannot receive. What happens if this one sends, if full duplex also sends? That's a problem. There will be a collision. The frames will be dropped. We lose information. What happens if one end of the system is 100 megabytes per second and if another is 100 gigabytes per second? If I'm sending to this side, no problem. If I try to push 100 gig to this side, that's a problem. Especially if you don't have my buffers, which you are likely not going to have, which can contain this amount of traffic. So we are talking about this so that we can introduce what we call auto negotiation, which when configured, can a system in a half duplex only, in a full duplex. Auto negotiation means this one can change your half so that it matches the other end. Panapo, kana pane auto negotiation configured on the link, rinochinja rovhuraita 100 megabytes. Because kana uchikwanisa push 100 gig, you can definitely push 100 megabytes. Kana afanana kudai so, then we are not going to have a problem. If we don't have auto negotiation, then you need to manually configure. You need to confirm what is the duplex settings of link rank, the port on one end and the other end. And you manually configure ese afanane. Akasafanana, that's a problem. So you can manually as well configure the bandwidth, the speed of a port, so that they are the same for the two ports anengari per link. Duplex and speed settings. The duplex mismatch is one of the most common causes of performance issues on 10 or 100 megabytes per second Ethernet links. It occurs when one port of the link operates at half duplex and the other operates at full duplex. We've touched on that. I think we've already touched on this. And here we're explaining collisions. This one is in full duplex, this one is in half duplex. There is bound to be a collision because this one cannot simultaneously send and receive. We've touched on this one. Auto MDX connections between devices once required the use of either crossover or straight through. The type of cable required depended on the type of interconnecting devices. So in legacy Ethernet networks, older networks, we had different type of cables required when connecting different type of devices. So can I connect a PC to a switch? I'll use a straight through. And if I'm connecting a switch to another switch, I'll use a crossover cable. If I'm connecting to another PC, I use a straight through. That was for legacy networks, Ethernet networks. But with the introduction of auto MDX, automatic medium dependent interface crossover feature, with the introduction of that, the auto MDX can automatically detect the type of cable connected, then adjust the internal wiring to ensure we have proper communication regardless of the cable type. You can see, if you look at Patakaitama standards 8568 A and B, cables atiri kushandisa, they are the same. What we are just differing was connections, variations, connections, pairs edu. When you are using these standards and you want to terminate with an RJ45, for example, cables wangauroshandisa, they were the same. Arrangement pairs ndo yanga yakatosiyana chete. So with auto MDX, it knows kuti ukashandisa for example panapa kudhara paishanda crossover, iwo ukauya ukaisa straight through, auto MDX zvainoita inochinja port iri, the internal, it adjusts the internal wiring yemaports aya, so that you can still communicate over this straight through, even if you're communicating between two identical devices. Switch crossover ishanda kuti router it works there. So auto MDX is just a useful function which allows us, it is even when you are designing network yako per packet tracer, for example, it's very rare that someone uses crossover cable. Unongoshandisa straight through, because auto MDX will deal with that. And that is what auto MDX is. And with that, okay, we conclude topic yedu, module number 7, Ethernet switching. Any questions? Any questions for the guys?
Inini handichazonda nyatsorasikira papo ndapota ndachita nchidhoza ona, saka I think I will have to revisit it. I will have to revisit my videos. Today I'm tired.
Right, all good. I think the good thing in the O2, we are recording these sessions. You can always revisit them. If you see you have questions,
Yeah,
I think my sessions, they are very long. Believe me.
yeah.
It's your duty kuuya nepanyepo modzoka motarara panyepo.
The good thing ndekuti majority edu tinenge tamboita sei, tinenge tamboverenga like during the day, saka we just read ahead, saka zvimwe zvito changoita follow through chete, tangoita kungoona kuti pana zvinobvisisa papa ndepapi. But so far so
labs
good.
are piling manje.
Yeah.
My labs are piling.
Saturday we deal with all of them, not an issue.
Exam matonyora lini?
Saturday.